Hello, everyone. Day 11, one more to go after today. And today we're going to talk about data. Um, and I have to say, I was a bit surprised. I learned things I didn't know from this session and from all the sessions today. I find them fascinating. So this was delivered by Kaggle, Google, of course, owned by Google. And it's about empirical rigor at scale or how not to fool yourself. There were surprising, implications that I had no idea. And the biggest fear of every data scientist is leakage. And apparently, we seem to have been fooling ourselves for a long time. Looks like. So, oops, sorry. If the data has ever been on the internet, consider it leaked. Any difference in test and training data is a leak. Any information about the future is a leak. And I think one of the reasons why YouTubers are selling their unused video footage to AI companies, we saw that before. It's not just, they buy it not just because they want to make money or they want to train models. They also want to test their models on data that they haven't really seen before. And these are challenges. I think they are most of them are well known. Model published trained on hidden data, synthetic floats had different precision, identical randomization, sorted order reveals information. These are all things that they can release. Synthetic noise successfully denoised, version of data published elsewhere, file names leaked information, and so on. Synthetic image aspect ratios. So sometimes the synthetic image can have an aspect ratio that is unique to that. And that kind of leaks the information. There's all sorts of weird pathology target circled in SARPy-Pen. It's all these problems that, if you ever work with data, you're going to find out are key. So the idea is, do you really memorize or you generalize? This is the big question. And you have to make sure that you generalize. Sometimes memorization can be good enough for you if you're trying to solve problems, especially in fraud, if you've seen it before. That's okay. But you really want to generalize. And we had a whole session about predictions on tabular data, and we've seen a lot of progress over there. But there's always the question, are they benchmarked properly? And I don't know, is that easy? You just take a standard tabular set, train split, you put it, and you get a prediction. And then here's the new reality. If the data has ever been on the internet or sent over the wire, consider it contaminated. So basically what they're trying to say, they have plenty of cases where you try something and on a data set that is public, and probably the model has been pre-trained on that, and you think you're generalizing, but the model remembers. And these are kind of like some new competitions that, in order to avoid that, what they basically do is they run the competition now, but the answers are going to be in the future. So even for the AI mathematical Olympiad, you kind of like solve them and you close, and then you reveal the answers. Okay. So for example, you know how DeepMind came up with this new paper for winning gold medals on Olympiads. I think they did try to make sure that it hasn't seen the problems before, but they're not quite sure. So the plan is to participate in the next Olympiad and see, brand new problems and see if they can actually get a gold medal. And if you notice on this WSDM camp, multilingual chatbot arena says a forecasting phase with a test set to be collected after the submission deadline You said expect this test set to contain at most 25,000 25,000 rows. So that's kind of like the new reality. So the Murphy law here is that Murphy law of empirical evaluation is that if a leak or contamination can happen, it will happen. Focusing on eliminating cheating helps ensure you don't accidentally cheat yourself. So using carefully constructed competition as evaluation is maybe a good idea. And there is this paper called SWE Bench, where basically it's supposed to resolve GitHub issues, where they collect issues now, and you kind of like create your prediction, and then once the issues are resolved by humans, then you reveal them to humans. It's an interesting talk, I think you're going to enjoy if you watch it. There was a tutorial. I actually have worked with one of the authors here in the past in a workshop, Roxy, advancing data selection for the foundation model from heuristics to principled methods. We talked about this was the signal, that these are the principles that lead us to what I call the language model scientists, that we're becoming more rigorous about that. And you might have seen this motto, AI is compute plus data. In fact, this could have been a Snowflake slide, because it says, Snowflake is supposed to separate data from compute. So I think Snowflake could use that. Maybe that's why they were branded as the AI data cloud, because of this decomposition. There's thousands of papers on optimization, model architectures, loss functions, but very few about data. And for a long time, research happened in the context of specific training data sets. So you got MNIST, CIFAR, ImageNet, and people were trying to improve the results of that. And I think at some point they were, overlearning and overfitting the data sets. And there was a generalization problem. And that was the best paper award at CHI. This is called Computer-Human Interaction. Everyone wants to do the model work, not the data work. And this is what people call data-centric AI. I think last year or 2 years ago, I can't remember, but there was a workshop at NeurIPS called Data-Centric AI, quite popular. Andrew and Z has been leading this, the data-centric AI resource hub. And that's basically where NeurIPS 4 years ago started the NeurIPS dataset and benchmarks track. So, and if you remember, there were about 460 papers on that track, focusing more on creating data. And we've seen throughout this series of talks, like the Dolma from Allen AI, the red pajama or the slim pajama, people create data sets, and they post them and they use them for training language models. But the problem is that it's very hard to find out which data set do you really need, because different evaluations and training protocols results in apple to oranges comparison. So not really, like, we need to put things in an order, and that's the paper that tries to systematize this process. You can see it has a lot of authors, among them my good friend Alex Dimakis, now at Berkeley. And the goal is to enable principal empirical comparison of different data curation strategies. This is part of the data-centric, like this tutorial summary, which is a benchmark for language model data curation, experiments to identify the key parts of an effective data curation pipeline. Sorry, this is from the paper Data Comp, not the tutorial. A state-of-the-art public training set for 7 billion parameter models. And basically, the way that it works, Data Comp, is that you have researchers with different compute budgets to participate. So you have models that, if you don't have that much computations for 400 million, 1 billion, 3 million, 7 billion, and 7 billion to X, I don't know what it means. And then, so this is the model parameters, and then you have the training tokens, and the trainer flops, and the 800 hours, the compute pool. And the idea is to find out how to curate your data set. So basically, even use it less. So you have the model, and you are trying to tweak. What you're tweaking is your data set, so that you can do it faster or with less data, with less tokens. And it says we develop our training set mostly at 1 billion 1x, 15x cheaper than the 7 billion 1x. So that's kind of like the idea. Then there is other initiative by NVIDIA, the Nemotron, transforming common crawl into a refined log horizon pre-training data set. Again, they're basically trying to curate the data set so that you get better performance. And for those of you who don't know Lion, 7 billion, I think it's a data set which is images and captions. It's very popular for diffusion models. So they try to rebuild Lion. So they're trying to rebuild a 5 billion data set, but this time publish not only the data set, but the entire tooling around it. And they set it up as a benchmark. Okay, and they say traditional ML benchmark data set fixed, improve the model, data comp, improve the data set, model training code fixed. And the conclusions, I think we pretty much said them. Training data is key for foundation models, both in language and vision domain. You mentioned that. Large language model improvements for better data curation. Data curation benchmarks such as data comp, LM enable rigorous experimental comparison of different data curation approaches. And model-based filtering, so far the most important processing steps. So removing data that are bad. A choice of training data for the filtering mode is crucial. Current methods are still ad hoc, and they need more empirical and theoretical research. Just wanted to remind you that when we were looking at the Allen AI, Olmo and Molmo, and the other one, the Pix, I can't remember the name, Pixmo, I think it was called, language models, they actually use some clever ways of synthesizing smaller, high quality data sets to achieve better results. So, we've seen a lot of examples so far. Now, we're going to go back a little bit in the spirit of, reducing leakage and making sure that the model generalizes. And this was a very interesting paper called Lingoli, a benchmark of Olympiad-level linguistic reasoning puzzles in low resource and extinct languages. So the idea is that, reasoning, of course, a key aspect of intelligence, but, benchmarking reasoning presents issues for construct validity. The data sets become contaminated or saturated. Memorization is both necessary and misleading. And, benchmarks rely heavily on construct validity. And people like the logic puzzles because we can validate them. And they don't have a lot of contextual knowledge. But it becomes even more interesting where you use low resource languages so that you make sure that the language model hasn't seen the same puzzle before, especially when it comes to Sudoku. And the answer is like, is reasoning sufficient to solve these tasks? As humans don't need to know the languages. School children can accomplish it. So whenever you use a low resource language, it means that you're relying less and less on the language skills and more on the reasoning skills. So they went ahead and they found, some languages like the Yawala Piti is an Arawakan language spoken by the Yawalapiti people in Zingu Park in Brazil. So they basically created puzzles in languages that very few people talk. And, who knows, maybe there's not even that much on the training data set. And here's some description of the benchmark. You can go and find out more. And you can see that, still the big language models prefer better. But they kind of like, they're being challenged. So anytime we find something challenging for language models is good. Okay, the next one that I want to talk about is there was another oral paper, the OpenMath Instruct one. Surprisingly, you see on the right side the OpenMath Instruct 2, because by the time it was presented at NeurIPS, they had already published or was under submission. They had the next version. So there's something interesting about that. There's lots of papers about generating math benchmarks, but here's what is very interesting. We'll figure out what it is. So, usually you have a question and you can write it in text solution or code interpreter solution. That's fine. And what happened is you can get pretty good accuracy. So you see that whenever the big ones like the GPTs perform much better with some few shot learning over Mixtral, and others. They're quite poor. And the idea is open source is it's not doing that great. So people want to create math data sets to training data to make them better. So what they do is basically GPT distillation. So what you do is you have a data set, you create more problems, you have a prompt, you put a few shots, and you solve new problems. So best open source models are all GPT distilled, fine-tuned solutions generated by GPT-4. MetaMath and Mammoth that you saw before do that. Okay, so I mean we're not stranger to that. DeepSeek probably did that. So using a bigger model to bootstrap a bigger data set and then distill it to a small one is great, except for one problem, which is becoming big. I hadn't thought about that before I saw that paper. Legal restraints. Distilled models can compete against OpenAI. So, if you take Mammoth and you create a language model and you put it out there and you sell it to students, you're immediately competing with OpenAI, and that's a legal problem, which, as far as we know, that's what happened with DeepSeek. They're kind of leveraging, if the allegations turn out to be correct, true. We don't know yet. But if that turns out to be, it's a legal issue, and probably they're hiding behind the fact that they can avoid the, legal battles because they're outside of the US. And of course, inference with GPT-4 can cost much higher than open source alternatives. We've seen that. And there's also lack of reproducibility. API behavior may change or become unavailable over time. So you build Mammoth now or MetaMath, you won't be able to reproduce it. So these are two benchmarks, the GSM 8K and the math. And this is how Mixtral is behaving. And it doesn't do as well as, well, it can be, if you keep resampling, you can do much better. But the problem is that these data sets are not, they're distilled. So no, actually, let me take it back. Math and GSMK come with reference text solution. Yes, actually, I take it back. You can use them, but the problem is you need to sample several times in order to get solution. So prompting the model with question, reference, solution list to increase training set coverage. But sometimes the problem is you can generate a nonsensical. So if you use this, this data set to create more synthetic solution, that's kind of like what it's getting is you might get not the answers that you want. But there is a better way, and that was basically the trick of the paper. So they took problems and they did masking. So they took numbers and they replaced 9 with M, and they basically yes, so they masked the solution. Okay, and that simple trick. So with that simple trick, they were able to basically generate questions and answers that are more generalizable. And they built the OpenMath Instruct one. And now you can see that the OpenMath Mistral 7 billion achieves much better solution, much better performance than before. And they are at par with the best GPT-4 distilled model. So MetaMath and Mammoth are GPT-4 distilled. Okay, so that's what you're comparing against. And yeah, so you can see that right now the people took basically so the GSM 8K and math are simple models. You take them, you fine tune them. Sorry, you generate more data with this simple masking trick, and you fine tune language models like Mistral 7 billion. And now you have the OpenMath Instruct, which has a much more permissive license. So sometimes people think about Llama and Mistral. Llama has a much more permissive license, and people want it. So the conclusion: the OpenMath Instruct 1, introduced in this paper, has 1.8 million question answering pair. It's at least 4 times bigger than prior work. Strong fine-tuning results, which are on par or better than the GPT distilled model. The dataset it's released with a commercially permissive license and has been widely used by the community. And what you should get from that is that you could use that that technique, that masking technique, to basically, I mean, we don't know how well it generalizes, but it's a nice trick. If you have a data set and you need to create more training data for fine tuning, that's a technique. That's basically a synthetic data generation technique. Okay, since we're talking about data, we we need to talk about this paper. It says, how many Van Goghs does it take to Van Gogh? Finding the imitation threshold. So the problem here is that, it's a copyright issue, which is when you say generate someone like Johnny Depp, is you want to generate something that looks like Johnny Depp, but it shouldn't really be Johnny Depp because you're having some copyright issues. Okay, and that's what the paper is dealing with, controlling the parameters, and it shows you some you basically have a knob over there of generating people who you want them to look like, but you don't want them to be the same. The copyright issue. And here's some extra references from the paper. We've talked a little bit about this one. This is a framework for analyzing data that that you're going to use for pre-training or fine-tuning. It doesn't know. So basically, this is a framework for finding out and cleaning up data sets. So you can find, domain distribution, PII, how much PII you're having based on different aspects, most common n-grams, contamination. So it's kind of like a data management system geared around. It can answer some specific questions. You can look at the paper, and then there is another paper that it could have been in the attribution domain. It's called Generalization versus Memorization, Tracing Language Models Capabilities Back to Pre-Training Data. I'm not sure why I put it in this section of the presentation, but that's kind of like another way. I think it's a little bit simpler than the one we saw with influence functions. Worth looking at. Again, probably I put it over there because it goes back to the distilling and cleaning up your data. And of course, we've seen that towards data efficient training large language model. I think it was in our previous talk where we talk about core sets. I'm not just going to repeat it. You can go back on that. Basically finding batches using much less data to get better performance. And we have about 10 minutes to finish with a very influential presentation, in my opinion. So this is something that was anticipated. So scaling LLMs with synthetic data loops, it's basically how Llama 3 was built. Okay, and I'll try to walk you through that. I do encourage you to watch the presentation. I think it's about an hour, actually 30 minutes long. So let's see here. Yes. So first of all, they ask this question: what is the purpose of post-training? It's something that we haven't really talked much about it. Like, pre-training is something that takes a lot of time and has technical difficulties. But a pre-trained model is not very useful. There's a lot of art on the post-training. And maybe another way to see that is that given your budgets, you can have a much bigger influence on post-training rather than pre-training. Let's put it that way. Pre-training is something that you're expected to do, like less people are expected to do. It's costly, and you should focus more on the post-training. And some of the reasons why you do post-training is reduce the likelihood of garbage at output, improve instruction following and reasoning, chain of thought capabilities, unlock new capabilities like tool usage, and more. And what this talk makes a point is that synthetic data is the backbone of continual post-training in frontier LLMs. So before 2023, this was kind of like the idea. You have the base model, after pre-training, and then you use supervised fine-tuning model, or what we call imitation learning. And then that was a human preference with a reward. And that was using, that was kind of like what people would call the aligned model. Okay, so two types of training: imitation learning and reinforcement learning, reward learning. Now, this is from the Llama 3 paper, a much more different, approach. It's more complicated, and you have models from previous rounds. You have a fine-tuning. You have a way of generating some prompts, K generation, per prompt. So you have some collected prompts, you generate data, you do some kind of rejection sampling, you put them back, you train a model, from your best model, you have another way of specialized pre-capability SFT data, SFT supervised fine-tuning. And then you also have pairways annotated and specialized pair capability preference data that you use the word model. This reinforcement learning, you do rejection sampling, you put them back. So it's a little bit of a complicated flow when we're trying to decipher it. So data loops, continuous development. The idea is that you're using the model. Trained models help build future models. You provide human model feedback iteratively and patch capabilities. And you have many times to get it right. So this talk is about broad overview of post-training Llama 3, data loops for post-training Llama 3, and open challenges for continual post-training. So the basic ingredients of post-training, again, we called supervised fine-tuning or imitation learning, preference tuning, DPO. So this is, I think the preference tuning, it's also, I don't know, I don't remember in this talk, but user preference tuning has to do with reinforcement learning as well. But maybe here they DPO and PPO, they separate them. I think, yeah. So the preference tuning, I think it's still reinforcement learning, but it has to do with human preference alignment. And the other is for developing specific capabilities like code and reasoning. Where in that particular case, you don't have a preferential data whether the human likes that or not, but whether it's correct or not. So far, we have seen that winning recipe is simple algorithms with careful data curation. Data loop 1, auxiliary models, aiding data development and model training examples. You have reward models. So the reward models are basically trying to predict whether a human would like it or not. You have LLM judges that you have a prompt response that you translate to chain of thought score label. You also have tool usage. Then you have the LLM classifiers that they're trying to rank different data based on difficulty and relevance. And the data loop 1, I don't know if we saw it's used extensively for data pruning, rejection sampling, data categorizations, and PPO. One of the things that they're using is the auxiliary models are brands for main runs. So they're usually initialized from newest checkpoints in each round. They use the aligned LLMs to label or generate training data. So you basically take your checkpoints and you're trying to filter out and get data that you like. You also use human annotations. But auxiliary models can go wrong. They can have stylistic biases, self-enhancement biases, and catastrophic forgetting. If you search the paper, they have lots of tricks that can help: better prompting, majority voting, fine-tune, and replay. This is another part of the data loop. Instruction and preference data generation. So rejection sampling, again, generate responses to prompts k times, use auxiliary models to rank the responses, use system prompts to guide data generation process. Prompts are human written or sometimes synthetically generated. I think it's becoming a little bit of of an art at this point, but I believe we're learning more. Each round brings new data. You need to manage, qualify, clean them up. Focus on highly difficult and highest quality data. I mean, what does quality data really mean? But what is the interaction between difficult and easy examples? So anyway, there's a recipe. I don't know if it makes sense to go through all these details right now, but as we've seen, so you get different types of data that they are generated in different ways, and you need to find the right mix to go to the next step. Now, of course, I have to say that Meta right now is kind of like some retrospective, and they're rethinking all this process because they see the competition from DeepSeek, and we don't know if DeepSeek actually went through all this process. And to be honest, we don't even know what stage did DeepSeek. DeepSeek is based on Llama, but we don't know if all these features were necessary for their success, how much they're working on top of that. Well, this is the slide that I really like. We've talked a lot about model merging. I've emphasized a lot how much I believe in combining smaller language models to solve tasks. And I don't know, that slide wasn't super highlighted by Meta, but it made me think, because I particularly like this approach. It says, it can be easier to make multiple bets on different data and then merge the final models in the end through techniques like parameter averaging. This is huge because you can decompose the problem. Remember, language models are suffering from this way of, this holistic view and this kind of like global and monolithic development. The biggest pro of this approach is that you can sometimes get the best of both worlds without worrying too much about data mixes, because you just trained 100 different models and you try combinations, you benchmark them. It's easy to brute force this ones and find which combination is the best. It does say that, which I don't understand. This makes the final model less reproducible, but I don't really agree with that, because if the way that you produce your language model is reproducible, then the mixing is also reproducible. I would put my eggs on that basket. So this is something that I keep an eye, because I think that this might be the way that we're going to work with language models in the future, because that's how we succeeded in building, huge software and all these companies. That computer science, was based on that principle. We never existed without this way of composability. That's another data loop. I don't know if we want to go through that. Specialized synthetic data. Again, it's another loop for specializing on tasks. And here's an example: generating hard programming with QA with feedback. Ask Llama to generate programming problem whose solution might be inspired by code snippets from pre-training. Prompt Llama to solve the problem in a given language, steering it to follow general rules of good programming. Require the model to provide chain of thought in comments. And then you use static parsers and linters, dynamic analysis to ensure correctness. And then you prompt Llama to revise the solution given the feedback from the parser. An interesting approach, something that you can use for your fine-tuning. As I said, there's lots of interesting ideas that have been proven in practice. And we're almost out of time, but we're finishing. This is another example: curate code from pre-training data, we prompt Llama to generate data that represents our target capability. Add comments and that's a task. Add comments and doc strings for the code snippet, and then you do back translate. That's an old technique. You prompt the model to back translate the synthetically generated data to the original code. So you give it the code, you ask it to put the documentation, and then you're trying to reproduce the code based on the documentation. So, and then you filter by using the original code as a reference to determine the quality of the input. How faithful is the back translated code to the original code? So you have a language model that is judging that. So that way you generate high quality data. And again, for specialized synthetic data, loops require strong models out of the box and creating prompting pipelines. Inductive bias is very important to prevent the model from going off the rails, and opportunities for continual learning from external grounding resources. And here's kind of like the limitations of synthetic data loops. Sometimes it's unclear how metrics will move with new checkpoints. Forgetting is still an issue. Self-enhancement and other biases may amplify. You can easily generate lots of garbage, so you have to have good verification. Loopy post-training might lead to better performance, but it's less reproducible and it can easily become quite complicated. I would agree, after seeing their presentation again and again, I want to say there's a few key points that you can kind of like take away from this presentation and say, well, I can try it in my case, but the whole process looks more of alchemy. Although I have to say the authors are trying to give all the details. There's like too many knobs, looks like, in this process. But again, I go back to the one that I liked, which is make more models and then combine them. That looks more rigorous. And, the closing takeaways, the best post-training recipes are loopy. So that loop, that feedback loop seems to be here to stay. Research will continue on that forum. And I think here, here we have some open problems. We can go through them. Better ways to ask utility data, tips, ways to combine and patch capabilities, how to get closer to continue a lifelong post-training. Interesting questions. And here we kind of like reach the end for today. Tomorrow it's going to be the 12th and last day of the series, which is going to be about math and coding.